Smoke is another effect of fire that we monitor. Most prescribed burns and wildfires will have a constraint or requirement related to smoke management that will guide our efforts in smoke observation and documentation. In addition, observation of smoke characteristics can provide useful fire behavior and safety information. Upon completion of this lesson, you should be able to describe and document smoke characteristics and recognize and report significant changes to fire line personnel and fire behavior specialists. You should also be able to recognize and report air quality concerns of interest to local air quality regulators. The tasks from the FEMO-FOBS Position Task Book that relate to this lesson include reviewing the project plan for smoke management requirements, and monitoring and recording smoke management information, including visibility problems and smoke characteristics. Why do we monitor smoke? The reasons fall into two categories. First, smoke gives us valuable information related to weather, fire behavior, and safety. Reading smoke gives us an indicator of wind direction and speed on the fire, warns us about changes in fire intensity, and tells us a lot about the stability of the atmosphere. The other reason we monitor smoke is to mitigate air quality concerns and comply with air quality regulations to protect public health and safety. First, we'll discuss what smoke characteristics can tell us about weather and fire behavior, and what important safety watchouts we can pick up from reading smoke. The smoke characteristics that we will be looking at are the color of the smoke, its dispersal direction and height, the formation and lifting of smoke inversions, and the characteristics of convection columns. A change in color indicates a change in fuels. Darker colors mean the fire has encountered heavier fuels. This fire has transitioned from a grass fire, lighter smoke on the right, to a timber fuel with heavier fuels and darker smoke. The dispersal direction of this smoke tells us the wind on this fire is blowing away from our vantage point, even if the wind where we're standing is blowing in a different direction. A wind-driven fire is a wildland fire that is controlled by a strong, consistent wind. In grass and shrub fuel types, wind-driven fires can have high rates of spread. In timber fuel types, spotting and crown fire are likely in wind-driven fires. Fires driven by upslope diurnal winds may change spread direction when the diurnal winds reverse. Smoke can tell you about upper-level winds. A column of smoke that rises up and abruptly changes direction with a 90-degree bend is called a sheared column. This means high winds aloft that may cause long-range spotting. These winds also have the potential to surface and cause sudden increases in fire behavior. The fire may be pushed rapidly in the direction of the wind shear, so working under a sheared column is a potentially hazardous situation. When the rising column bends backward over itself as the smoke rises, that's an indicator that the upper-level winds are blowing in a direction opposite that of the surface winds, sometimes called battling winds. These upper-level winds can potentially surface, causing sudden shifts of wind direction and speed of the fire. What would happen to firefighters located at the heel of this fire if the upper-level winds surfaced? Smoke rising straight up indicates an unstable atmosphere, meaning atmospheric conditions that promote the lifting of air currents vertically. Unstable atmospheric conditions are a significant factor in large fire growth. However, an unstable atmosphere causes smoke to rise and disperse better, leading to fewer air quality problems. To estimate the height that the smoke is rising, use nearby trees, power lines, or known elevation changes such as mountaintops to estimate the height. Inversions indicate a stable atmosphere. The atmospheric conditions resist vertical movement, and the smoke is trapped under the inversion layer. Inversions commonly occur overnight in mountainous areas and in coastal areas. They are of interest because they decrease fire behavior, but they also reduce ground-level visibility and air quality. To estimate the height of the inversion layer, again, you can use nearby trees, power lines, or the elevation of surrounding mountains. Smoke inversions are also of interest because the lifting of an inversion can cause a sudden increase in fire behavior. When an inversion begins to lift or break, the air mass is in transition from stable to unstable. The behavior of a fire burning beneath an inversion may change abruptly when the inversion breaks. An inversion lifts or breaks as a result of winds that mix and scour the stable air, or the heating and lifting effect of solar radiation as the daily temperatures warm up. Inversions tend to set a pattern for the time of day that they lift or break. Be aware of and document this pattern, as fire behavior will change accordingly. The lifting of inversions is also of interest for fire aviation resources, as the inversions often restrict their ability to fly or the effectiveness of their flights. The rising column of gases, smoke, fly ash, particulates, and other debris produced by a fire is known as the convection column. Depending on fire intensity and atmospheric conditions, the convection column might rise 100 feet or many thousands of feet. Vertical development of a fire's convective smoke column is influenced by 3 factors: fire intensity, stability of the lower atmosphere, and winds aloft. Fire intensity determines the vertical development of the fire and smoke column as the heat energy generated by the fire is released to the atmosphere. High-intensity fires create strong indrafts at the fire's edge, which can help feed a convective column that may build many thousands of feet into the atmosphere. With high-intensity fires, the fire can control the environment to a marked extent, and its influence can significantly modify weather elements near and adjacent to the fire, such as wind speed and direction and temperature. Stability of the lower atmosphere is evaluated using the vertical distribution of temperature. The atmosphere is considered stable if particles of air resist vertical displacement, meaning convection is suppressed. If the lower atmosphere is very unstable, it allows for more vertical movement of air, which can contribute to the development of large fire plumes. Winds aloft refer to those winds affecting the convective column. Strong winds tend to discourage vertical development of convective columns and can bend the smoke column so that it stays near the ground as smoke travels away from the fire. These leaning columns are typical of wind-driven fires and may lead to rapid rates of spread and short-range spotting. Stable air and/or strong winds tend to discourage vertical development of convection columns. A plume-dominated fire can occur in unstable conditions when the power of the fire becomes stronger than the power of the local winds. Such fires are extremely unpredictable, spread in various directions simultaneously, and exhibit intense burning conditions. In normal fire conditions, smoke rises and disperses without noticeable impacts on fire behavior. However, when the convection column intensifies to a level such that air rushing into the column base to replace the air leaving the top of the column is stronger than the ambient wind field, a fire may create its own wind and greatly increase fire behavior independent of the ambient wind. The rush of air entering a convection column may transport firebrands up and out of the column, causing spot fires. When the color of the column changes from light to dark, it is an indicator that the fire intensity is building. These high-intensity plume-dominated fires can develop central convective columns with counter-rotating vortices that involve massive entrainment of the surrounding air mass. This stage of fire can produce fast-rising plumes and turbulent downdrafts that can exacerbate an already dangerous situation. The downdrafts and fallout from the column carry sparks and embers that ignite new fires. The column will begin to rotate faster as the fire intensity increases, and fire behavior will become more erratic. On the Indians' fire on the Plumas National Forest on June 11, 2008, at approximately 1550 hours, firefighters along the east edge of a burnout operation were observing a large, rotating fire plume that seemed to be paralleling the burnout operation. Video footage taken during this time clearly shows this rotation. Later interviews indicate that firefighters had observed such phenomena before, but did not perceive this event to be enough of a threat to safety to warn others. The rotating vertical plume appeared and behaved in many aspects like a moderate-intensity tornado, approximately 1,000 feet in diameter at the base, and 1,000 to 1,500 feet tall. Winds at the plume base were estimated at greater than 70 miles per hour and resulted in extreme fire intensity and significant wind-caused damage. Branches with base diameters as large as 18 inches were torn from trees and transported through the air. At approximately 1624, an engine crew was engulfed in thick smoke, strong winds, and continuous ground flames when the rotating plume crossed the road. Flame length was undetermined, but flame height was reported to be knee-high. and it ignited numerous spots that quickly grew together. The engine crew attempted to withdraw from the area toward their engine, and in this process, the hot temperatures caused them to deploy their fire shelters. 3 of the crew successfully removed the shelters and wrapped them around their backs while continuing efforts to exit the area. The 4th crew member had difficulty deploying his shelter and continued running until he reached the engine. 1 crew member with serious burns was flown to a burn center, and 2 others were transported by ambulance to a local hospital. The most seriously injured crew member remained in the burn center for more than a week. The 2 other crew members were treated and released. The Accident Prevention Analysis Report on the Indians' fire included these 2 key findings. Although other resources observed the rotating vertical plume, there was hesitancy between crews to communicate the hazard to other fireline personnel. Crews underestimated the hazard presented by the plume. Rotating plumes present a significant hazard to fire personnel. Observations of a rotating plume should be communicated to surrounding personnel, and the potential for the plume to move and spread fire erratically must be considered when choosing tactics, escape routes, and safety zones. As high-intensity fires cool, however, the central column often collapses. Wind shifts, which temporarily cut off the source from the updraft before a new one can become established, can also lead to column collapses. A collapsing column will produce strong, erratic downbursts of wind in all directions. The downdrafts can also bring heavy smoke to the surface, decreasing visibility and firefighter safety. If a fire has a well-developed column and you feel a light rain on the fire line or experience a sudden calm, you can expect downbursts. Watch this time-lapse video of a plume-dominated portion of the Zaca fire in California in 2007 and look for the signs as the columns form and collapse. Every time the column collapses, all that air, moisture, particulate matter, and debris fall to the ground and create erratic winds in the form of downdrafts. The column's collapse, once the heat generated at the surface by the fire is no longer sufficient to maintain an updraft. This situation can happen at potentially any time, and columns may go through many collapses and regeneration stages in any given day. And here's another telltale sign of impending collapse. If a column once looked impressive and no longer does, pay close attention, a collapse may be imminent. We've discussed what you can learn and anticipate about weather and fire behavior by reading smoke. Much of what we've discussed involves warning signs of hazardous fire conditions. As a FEMO or FOBS, or as any fireline resource personnel, one of the critical responsibilities of your position is to communicate important changes to your crew and your supervisor. Significant smoke observations to communicate immediately include changes in wind direction or speed, sheared or leaning columns, changes in smoke color, lifting of an inversion, a developing convection column, a collapsing column, and/or a rotating column. We'll also discuss documenting these observations for your report at the end of this lesson, after we discuss making air quality observations. Air quality is defined as a measure of the pollutants in the air in terms of the healthiness and safety of the atmosphere. As fire managers, we're concerned about air quality because particulate matter in the air we breathe can be a health hazard for both fire personnel and the public. Poor visibility can negatively impact aviation resources on the fire incident, traffic safety in the vicinity of the fire, and scenic resources many miles around the fire. Smoke in the air can lower visitation rates at these scenic areas and affect the local economy. And finally, the public's interest in air quality is protected by local air quality regulators whose mission is to prevent and mitigate the negative effects associated with air pollutants, including smoke from wildland fires. As a FEMO or FOBS, your observations of air quality related to fire activity can help fire managers and air quality regulators mitigate these health and safety concerns and ensure compliance with air quality regulations. Smoke production from a wildland fire can last from less than 1 hour to several weeks. The total volume of smoke produced from a fire depends primarily upon the amount of fuel consumed. Downwind concentrations of the particulate matter in smoke are related directly to the amount of fuel being burned and the rate at which it is burned. The manner in which combustion and smoke production takes place depend primarily on the fuel moisture and physical fuel properties such as fuel size, fuel arrangement, and total amount of fuel. Can you see how your observations of the fire environment might be helpful to analysts in predicting smoke production and concentrations of particulate matter? The purity of the air we breathe is essential to our health and the quality of our lives. The smoke from wildland fire can have adverse effects on both. As touched on earlier, one of the biggest dangers of smoke comes from particulate matter, which are solid particles and liquid droplets found in air. In smoke, these particles are often very tiny, smaller than 2.5 micrometers in diameter. How small is that? Think of this. The diameter of the average human hair is about 30 times bigger. These particles can build up in your respiratory system, causing a number of health problems, including burning eyes, runny noses, and illnesses such as bronchitis. The particles also can aggravate heart and lung diseases, such as congestive heart failure, chronic obstructive pulmonary disease, emphysema, and asthma. 80 to 90% of wildfire smoke, by mass, is within this fine particle size class, known as PM 2.5, making public exposure to wildfire smoke a significant concern. Asthmatics, the elderly, those with cardiopulmonary disease, as well as those with pre-existing infectious respiratory disease, such as pneumonia, may be especially sensitive to smoke exposure. Children and adolescents may also be especially susceptible to ambient particulate matter effects due to their increased frequency of breathing. In children, studies reveal associations of particulate exposure with increased bronchitis symptoms and decreases in lung function. Monitoring the movement of smoke can help air quality regulators, health departments, and others provide advance notifications to these smoke-sensitive populations, allowing them the opportunity to temporarily relocate to less smoky areas. Wildland firefighting presents many hazards to fireline workers, including smoke inhalation. Firefighters can face unhealthy levels of smoke when patrolling or holding fire lines on the downwind edge of a wildfire or prescribed fire, during direct attack of an escaped prescribed fire, or while mopping up. Many experienced fireline personnel consider this to be only an inconvenience, occasionally causing acute cases of eye and respiratory irritation, nausea, and headache. But the less obvious effects may be of greater concern. The potential for impaired judgment and long-term health impacts, especially when large-scale fires occur in terrain and atmospheric conditions that force fireline workers to work for many days in smoky conditions. Days or weeks of smoke exposure are problematic because of the cumulative effect of carbon monoxide exposure, and the lungs' ability to sweep fine particles out of the respiratory passages may be suppressed over time. The effects of smoke exposure may also be intensified by some common aspects of firefighting, such as hard breathing, extended hours, and high elevations. Accurate observations of smoke production and dispersion can help fire managers make appropriate plans to move fireline resources to less smoky areas, rotate fireline personnel out of areas with heavy smoke, and locate sleeping areas in places that minimize additional exposure to smoke. The reduction in visibility due to smoke affects fire aviation resources as well. Smoke inversions can ground helicopters and decrease the effectiveness of aerial reconnaissance missions. Good information about the lifting of an inversion can increase the efficient and timely use of an expensive resource. Unanticipated increases in smoke production can also limit pilots' ability to visually detect nearby aircraft while in flight. Reduction of visibility from wildfire smoke is a significant concern in traffic safety. Smoke and smoke-induced fog obstructions of visibility on highways can sometimes cause accidents with property damage, personal injuries, and loss of life. During 2000, smoke from wildfires drifting across Interstate 10 caused at least 10 fatalities, 5 in Florida and 5 in Mississippi. Communicating changes in visibility that will affect roadways allows public safety personnel to close affected areas and alter traffic patterns to avoid highway accidents due to smoke-impaired visibility. Visibility is the optical clarity of the atmosphere. It is usually expressed as the distance a small object can be just distinguished from a light background. Visibility protection is an important goal of smoke management. This picture shows a vista from Yosemite National Park taken on a good visibility day. Here's the same vista on a day with poor visibility. The Clean Air Act of 1977 established areas known as Class 1 airsheds to protect the visibility of national forests, national parks, and wilderness areas. Smoke from wildland fires can obscure views of these natural wonders. Every year, there are over 280 million visitors to our nation's wilderness areas and national parks. Congress has set these special places aside for the enjoyment of all that seek spectacular and inspiring vistas. Unfortunately, many visitors are not able to see the beautiful scenery they expect. During much of the year, a veil of haze often blurs their view. The haze is caused by many sources of both natural and man-made air pollution, including wildland fire. At the Grand Canyon, 82% of 638 respondents rated clean, clear air as very important or extremely important to their recreational experience. 3 National Park Service studies determined that air quality conditions affect the amount of time and money visitors are willing to spend at national parks. Park visitors generally responded that they would be willing to spend more time and money if visibility conditions were better, and, conversely, less if visibility conditions were worse. Some small communities depend largely on these tourism dollars to support their local economies. The importance of these specially designated scenic and recreational areas, both culturally and economically, often qualifies them as smoke-sensitive areas. A smoke-sensitive area is defined by the National Wildfire Coordinating Group as an area that may be adversely affected by smoke from wildland fire. Examples include public roads, airports, populated areas, and areas with existing air quality or visibility problems, called non-attainment areas, if their air quality currently does not meet federal standards. Smoke-sensitive areas are defined individually by states and tribes in their smoke management plans, so the terminology and definition will differ by state or reservation. Let's look at an example. The state of Colorado uses the term smoke-sensitive sites and defines them as Class 1 areas and other locations of scenic and or important vistas, especially during periods of significant public use, urban and rural population centers, schools, hospitals, nursing homes, transportation facilities such as roads and airports, recreational areas, and other locations that may be sensitive to smoke impacts for health, safety, and or aesthetic reasons. We've discussed some of the health, safety, and social concerns that might cause an area to be considered smoke-sensitive. Communication with local air quality regulators can help fire managers identify the specific areas of concern and document the impacts of smoke production on them. This information makes fire managers aware of the people and places that may be affected by the smoke event, and prompts the local air quality regulators to consider implementing additional protective requirements, such as instrument-based monitoring and public notification. Your observations and documentation of smoke production, direction of dispersal, and visibility impacts play a vital role in maintaining effective relationships between air quality representatives and fire management organizations. Smoke management programs vary by state, tribe, and sometimes by county. The purposes of these programs are to 1. Minimize the amount of smoke entering populated areas, thereby preventing public health and safety hazards, such as visual impairment on roadways or runways, and problems at sensitive areas, such as nursing homes or hospitals. 2. Avoid significant deterioration of air quality. And 3. Eliminate human-caused visibility impacts in Class 1 areas. Smoke management requirements should be specified in the burn plan or wildfire management decision. You should review these requirements with your incident supervisor to ensure you understand what you will need to observe and document to comply with the requirements. As with the other forms FEMOs and FOBs use to document their observations, no standard interagency form exists. Air quality regulators may have specific smoke observation forms to be used in their area. Check with your incident supervisor to ensure you are using an acceptable form. Communicate any required information to air quality regulators through your supervisor. Effective communication of these observations can help fire managers and air quality regulators mitigate health and safety concerns and ensure compliance with air quality regulations. Your observations of smoke characteristics are crucial to complying with air quality regulations, mitigating impacts on smoke-sensitive areas, and increasing situational awareness of potential fire behavior among fireline personnel. In summary, in this lesson we covered how smoke observations can provide valuable information about fire behavior. We discussed critical changes in smoke characteristics that indicate hazardous increases in fire behavior, and the importance of communicating these warning signs to other fireline personnel in the area. We also talked about how air quality affects the health and safety of fire personnel and the public. And finally, we explained how effective communication of smoke observations from wildfires and prescribed burns can help mitigate health and safety concerns and ensure compliance with air quality regulations. Minimizing the adverse effects of smoke on human health and welfare while effectively managing wildland fire is a collaborative activity. The FEMO and FOBS positions contribute to this process by providing accurate and well-documented observations of smoke characteristics, production, and dispersal from wildland fires and prescribed burns.